So in this section of notes, we're going to start by thinking about the following problem. The problem says, suppose 40% of people have blonde hair and 20% of people have blue eyes. What proportion of people have both blonde hair and blue eyes? So the first thing to notice about this question is actually we don't know the answer. There isn't enough information in the question to tell us what proportion of people have both blonde hair and blue eyes. However, if it were the case that having blonde hair didn't affect whether or not you had blue eyes, then, if that were the case, then we would be able to solve the problem. So, the answer here is, don't know. But, if it were the case that having blonde hair, having blue eyes were unrelated, then we could answer it right. Because saying that 40% of people have blonde hair and 20% of people have blue eyes, then we'd be saying, well, the 20% of blue-eyed people makes up 20% of the blonde-haired people and 20% of the non-blonde-haired people, because it would be, distributed in the same proportion in each. So if this were the case, then the blue-eyed people would make up 20% of the blonde-haired people and 20% of the non-blonde people. So here, 20% of the blonde people, well, the blondes are 40%. 20% of 40%. 20% of 40% is 0.2 times 0.4, which is 0.08, or 8%. So, if it were the case that having blonde hair and blue eyes were unrelated, then 20% of the 40% of blonde people would have blue eyes. Thus 20% times 40% would have both, which is 8%. And so what we've got there is an example of a concept known in probability as independence. And what we've just said there is we're saying that if blonde hair and blue eyes are independent, that is, we don't think they're related, then the proportion of people, or if you like, the probability of a random person having blonde hair and blue eyes would be equal to this 20% of 40%, which is multiplying the proportions or the probabilities. Probability blue eyes times probability blonde hair. And so that's this concept of independence in probability, that two events are independent if to get their and we multiply them together. So let's write that as a proper definition. So the definition is two events A, B are independent if the probability of both of them happening is the product of the individual probabilities. Okay, so that's the definition of independence. So there are basically two useful ways we can use this definition of independence here. One way is that if we are told probability of A, and we are told probability of B, and we are told probability of A intersect B, we can work out whether or not those events are independent. Because if multiplying together the two individual probabilities gives you the probability of the intersection, then we satisfy this definition and we're independent. Whereas if they're not equal, then we don't satisfy this definition and they're not independent. So we can work out whether or not events are independent or not by checking the probabilities. The second way is we might be told the individual probabilities, PA and PB, and we might also know that the events are independent. And in that case, we could work out the probability of the intersection because we could multiply the two individual probabilities because we know we have independence. Now, there's kind of two ways that we could know events are independent. One is there could be a question that said, assume this and that are independent, then what's the probability of their intersection? And we know we'd have to multiply them together. The other way is that we might assume they're independent because we don't think they've got anything to do with each other. So, for example, if we toss a coin and then roll a dice and say, what's the probability we get a head on the coin and a 5 on the dice? Even if the question doesn't say they're independent, we might assume they're independent because there's no way for the coin to affect the dice. So we might be told independence, or we might assume it because of a kind of lack of physical relationship. Let's see two examples of those two different ways that we can use independence in a question. So the first example is assume we're rolling a dice and our events are A, that we get an even number, which of course is the possibilities 2, 4 or 6 on a normal 6-sided dice, and let B be the event that we get at least 4. So on a dice, that's the possibilities 4, 5 or 6. And we want to know, are these two events, A and B, independent or not? Well, we know, of course, that the probability of A is 3 possibilities out of 6, or a half, and the probability of B is also 3 possibilities, 4, 5 or 6 out of 6, which is a half. What about A intersect B? Well, A intersect B is the set of outcomes that are in both A and B. And if we look at they're 2, 4, 6 and 4, 5, 6, so the things in the intersection are 4 and 6. Those are the only two outcomes that are both even and at least 4. And so the probability of A intersect B is 4/6, or 2/3. So the question is, do these satisfy the definition of probability? Well, no, they don't, right? Because probability of A times the probability of B is a half times a half equals a quarter. I just realised I've made a mistake in the previous line. A intersect B was 2 possibilities out of 6, which was 1/3. Sorry about that. But we see that the probability of A intersect B is a third, and the probability of A times the probability of B is a half times a half equals a quarter. And so those are different. So those two events are not independent. Because if they were independent, the probability of the intersection would be the product of the probabilities, and that hasn't happened. So that's where we had all 3 probabilities, and we used them to find out whether or not the events are independent. And here we found out that they weren't independent. Another example, let's say we have a biased coin that's heads with probability P, and tails with probability 1 minus P. And we're going to toss the coin 3 times, and what's the probability we get exactly 2 heads? And it seems fair to assume that these 3 coin tosses are independent, right? Because we're going to do them one after another separately. I want to know what's the probability of exactly 2 heads. Okay, well, how could we get 2 heads? We could get this as head, head, tail. We could get this as head, tail, head. We could get it as tail, head, head. That is, the tail could be the first, second, or third coin, and the other 2 would have to be heads. So, for example, probability of head, head, tail is the probability that the first coin is heads, and the second is heads, and the third is tails. But because they're independent, because we're told these are independent, we can split this up into multiplying. So it's the probability the first is head times the probability second is heads times the probability the third is heads. And we can do that because they're independent. We can't always do that, but when we have independence, we can do that. And so that's p times 1 minus p, or p squared 1 minus p if you prefer. And similarly, the same way, albeit in a different order, we also get the probability of head, tail, head, and the probability of tails, heads, heads is also p squared for 2 heads and 1 minus p for a tail. Again, because of independence, allowing us to multiply the probabilities. And so finally, probability that we get 2 heads is head, head, tail, or head, tail, head, or head, tail, head, head. And those 3 events are disjoint, so we can add them up. It's head, head, tail plus probability head, tail, head plus probability tail, head, head. So that's p squared 1 minus p 3 times. So we get 3p squared 1 minus p. So note that when we did this question, up here we used independence to allow us to turn the and into multiplying. Down here we used disjointness to allow ourselves to turn the union into a sum without having to subtract any intersections. And so that's the other way that we can use independence, this idea that 2 things aren't related, the idea of independence, to help us solve problems in probability.